All right, let's dive in. Today we're going to talk about the invisible shield that protects pretty much everything you do online. Cryptography. It's the secret science that keeps our digital world safe, and we're going to crack it wide open.
Now, I know this can sound super complicated, but don't worry. Think of this as your cheat sheet for online security. We're not getting lost in the mathematical weeds. We're just pulling out the big ideas to show you how it all really works.
Because every time you buy a coffee, send a private message, or check your bank account, cryptography is the unsung hero working behind the scenes. So let's start at the very beginning.
Okay, so to really get a grip on this, we have to start with the core idea, which, believe it or not, goes back thousands of years. What exactly is secret writing?
Well, the word itself actually comes from the Greek for, you guessed it, secret writing. And that's what it's all about. It's the science of taking normal, readable information, what we call plain text, and scrambling it into a totally unreadable format called ciphertext.
But modern cryptography is about so much more than just secrecy. It really has four big goals. First, you've got confidentiality. That's the classic one, keeping secrets secret. Then there's integrity, which guarantees the message hasn't been messed with. Authentication proves who sent the message. And finally, non-repudiation, which is just a fancy way of saying they can't deny sending it later. The whole package creates digital trust.
So, how does all this scrambling and unscrambling actually work? Well, it all boils down to the most important part of the whole process, the keys.
Here's a good way to think about it. An encryption algorithm builds a complex digital safe. It can lock up your information perfectly, but it's completely useless without the one thing that matters, the right key to open it. And this idea of keys leads us to the two main flavors of encryption. First, you have symmetric. It's super simple and very fast. It uses one shared key to both lock and unlock the safe. The catch? How do you share that secret key securely in the first place? That's where asymmetric comes in. It's really clever. It uses a pair of keys, one public and one private. It completely solves that sharing problem, but, and it's a big but, it's much, much slower. So you've got this classic trade-off between speed and security. So, with those two core concepts, one key or two, we can build this entire toolbox of cryptographic tools that, believe it or not, we all use every single day.
Let's run through the greatest hits, shall we? For symmetric encryption, the gold standard is AES. That's likely what protects your Wi-Fi right now. The workhorse of asymmetric is RSA, which is used for securing websites and making digital signatures. Then you have hash functions, like SHA-256, which create unique digital fingerprints for data. And all of that comes together to create digital signatures, which act like a modern, tamper-proof wax seal.
Let's zoom in on hashing for a second, because it's absolutely crucial for data integrity. A hash function can take any input, a password, a huge document, or this very sentence.
And it runs it through an algorithm to spit out this unique, fixed-length string of characters. This is the data's fingerprint. And here's the crucial part. It's a one-way street. You can't go from the hash back to the original text, ever. And if you change even a single comma in that original sentence, the output hash will be completely different.
But of course, the second you build a better lock, someone else starts working on a better lockpick. This brings us to the constant battle between cryptographic defenses and the attacks designed to break them.
Attackers might use brute force, which is just what it sounds like, trying every possible key until one works. Others are sneakier, using side-channel attacks to exploit tiny physical information leaks from the hardware itself, or man-in-the-middle attacks to secretly intercept messages. But often, the weakest link isn't the math at all, it's us. Social engineering is just the art of tricking a person into handing over the key.
So how do we fight back? Well, the defense is really all about diligence. It means using strong, vetted algorithms like AES, managing your keys securely, and always keeping your software updated. But for passwords, there's a specific, brilliant technique we need to talk about.
It's called key stretching. The idea is simple, but it is so powerful. Instead of hashing a password just once, you do it thousands or even millions of times. This makes the process deliberately slow for a computer. So a single password guess that might take a microsecond for an attacker suddenly takes a full second. That slowdown makes those brute force attacks practically impossible.
Okay, so let's see how this all comes together in the technology we use every day, because this isn't just theory, it's the absolute bedrock of our modern digital infrastructure. Take blockchain, for instance. Its security relies entirely on these tools. Every block of transactions gets a unique hash, its fingerprint. The next block in the chain then includes the previous block's hash.
This creates an unbreakable, interlocking chain that's impossible to tamper with. If anyone tries to alter an old block, its hash changes and the whole chain breaks for everyone to see.
And you don't even have to look for this technology. It's right there on your computer. Powerful full-disk encryption is built right into your operating system. On Windows, it's called BitLocker. On macOS, it's FileVault. They use these same principles to protect every single file on your computer, automatically.
So, the cryptography we have today is incredibly robust, built on decades of brilliant research. But the digital world never stands still. The next great challenge is already on the horizon: quantum computers, with the potential to break many of our current systems. The race is on to build the next generation of quantum-resistant cryptography. What will that future of secrecy look like? Now that's something to think about.